Welcome to the channel. In this video, I want to invite you to slow down with me and take a long, careful walk through an idea that quietly shapes almost everything we experience, even though most of us rarely stop to think about it. That idea is gravity. Not gravity as a dramatic force, not gravity as something that pulls or commands, but gravity as something far more patient and far more fundamental than we are usually taught to imagine. We use gravity every day without noticing it. It keeps our feet on the ground, our atmosphere wrapped around the planet, and our world stable enough for life to exist at all. And because it is always there, it tends to fade into the background. Gravity becomes obvious only when something goes wrong, when something falls, or when something collapses. But in reality, gravity is doing its work even when nothing appears to be happening. In this video, I want to explore gravity not as an event, but as a process, not as something that acts, but as something that shapes. Gravity, at its core, is about geometry. It is about the structure of space and time themselves, and how that structure quietly guides motion over long periods of time. Once you begin to think of gravity this way, many of the questions we usually ask about it start to change. Most of us learn early on that gravity is a pull. Objects fall because they are pulled downward. Planets orbit because they are pulled inward. Stars form because matter is pulled together. This picture is simple, and for many everyday purposes it works, but it also hides something important. It suggests that gravity is actively reaching out and doing something to matter, when in reality gravity is better understood as the environment matter moves through. In modern physics, gravity is not a force in the same sense as electromagnetism or the nuclear interactions. Instead, mass and energy change the shape of space and time, and everything else responds by moving along paths that are consistent with that shape. Objects are not being dragged toward a center. They are following the straightest possible paths available in a curved space-time. Gravity is not telling them where to go. It is limiting where they can go. This difference may sound subtle, but it has enormous consequences. Forces can be resisted, redirected, or canceled. Geometry cannot. You can push against a force, but you cannot push against the shape of the ground beneath your feet. If space and time are curved, motion will follow that curvature whether anything intends it or not. Gravity is powerful not because it is aggressive, but because it is unavoidable. This video is long by design, because gravity does not reveal itself quickly. Gravitational processes unfold over immense stretches of time. Stars take millions of years to form. Galaxies take billions. Even the most extreme objects in the universe are the result of slow, cumulative processes rather than sudden events. If we rush through gravity, we miss what it is actually doing. Over the course of this walk, we are going to build a picture piece by piece. We will look at why gravitational collapse is usually slow rather than fast, and why that slowness is essential for structure to exist at all. We will explore why rotation appears naturally once matter begins to gather, and why that rotation leads almost inevitably to disks instead of simple spherical piles. We will also look at why almost nothing in the universe ever falls straight inward, why structure carries memory of its past, and why collapse tends to occur in stages rather than all at once. Along the way, we will talk about extreme objects like neutron stars and black holes, not as dramatic shortcuts or failures of physics, but as endpoints in a long, orderly geometric process. Later in the walk, we will step back far enough to see how gravity reshapes time itself, and why that matters not just for individual systems, but for the future of the universe as a whole. Gravity is not just about where things move. It is about how long things last, how change accumulates, and how persistence becomes possible. Throughout this video, I will try to explain my thinking as clearly and honestly as I can, without pretending there are final answers where there are not. This is not about proving a single model or arguing against alternatives. It is about understanding what gravity cannot help but do once matter exists and time is allowed to pass. Think of this less as a lecture and more as a conversation. You do not need advanced mathematics to follow the ideas, and you do not need to agree with every framing to see the structure of the argument. All that is required is patience, because gravity itself is patient, and it rewards careful attention. If you stay with me through this walk, my hope is that gravity will start to feel less like a mysterious force and more like a quiet, reliable presence. Not something that pushes the universe around, but something that shapes the paths everything must follow. Once you see gravity this way, many familiar patterns begin to make sense, not as accidents or coincidences, but as natural consequences of geometry unfolding over time. In the next section, we will take the first real step into that geometry itself. We will talk about gravity not as pull, but as shape, and why that single shift in perspective quietly explains far more than it seems at first. Section 2, Gravity as Geometry, Not Pull. When we say that gravity is geometry rather than pull, we are making a quiet but profound shift in how we understand motion itself. Instead of imagining gravity as something that reaches out and acts on objects, we begin to see it as the shape of the environment those objects move through. Nothing is grabbing matter and dragging it inward. Matter changes the structure of space and time, and motion unfolds according to that structure. Gravity is not an action. It is a condition. To make sense of this, it helps to step away from the idea that objects are trying to fall. In physics, objects do not try to do anything. They simply move along paths that are available to them. In a flat environment, the straightest possible paths remain straight. In a curved environment, those same straight paths bend, even though the object itself feels no force pushing it sideways. Gravity is the name we give to that bending when it is caused by mass and energy shaping spacetime. This is why gravity behaves so differently from the forces we encounter in everyday life. When you push an object, you can feel the resistance. When a magnet pulls on metal, there is a clear interaction, but an object in free fall does not feel gravity at all. It feels weightless. That is not a flaw in the theory. It is the clue. The object is not being pulled. It is moving freely along a path that happens to curve through space and time. Once this idea settles in, many familiar features of gravity start to look inevitable rather than mysterious. Gravity affects everything equally, not because it applies the same force to every object, but because everything shares the same geometry. A feather and a stone fall together in a vacuum because they are following the same curved paths, not because gravity treats them the same way. The differences we see in air come from resistance, not from gravity itself. Geometry also explains why gravity cannot be shielded or turned off. You can block a force, you can redirect a field, but you cannot isolate yourself from the shape of the space you occupy. If space-time is curved, everything within it must respond. Gravity is universal not by design, but by necessity. It applies to anything that exists, because anything that exists participates in geometry. Another important consequence of this view is that gravity does not point toward anything. There is no arrow saying, "This way is down." The geometry simply defines which motions remain consistent and which do not. Objects do not move toward a center because the center is calling them. They move the way they do because paths that wander too far away become harder to sustain over time. This removes intention from the picture entirely. Gravity does not prefer inward motion. It does not seek equilibrium. It does not aim for collapse. It only defines constraints. Motion unfolds within those constraints, and over long periods of time, certain outcomes become more likely than others. Geometry also explains why gravity is so weak at small scales and so dominant at large ones. A small mass bends space-time only slightly. The resulting curvature barely changes the available paths, so motion looks almost straight. But as mass accumulates over larger regions, those tiny curvatures add up. Over long distances and long times, geometry quietly reorganizes motion. Gravity does not overpower other interactions. It outlasts them. This is why gravity sets the large-scale structure of the universe without interfering with the details of chemistry or atomic physics. Electromagnetism binds atoms. Nuclear forces shape nuclei. Gravity provides the background those processes unfold within. It determines where matter gathers, how systems move relative to one another, and how long structures can persist. Seen this way, gravity is not competing with other forces. It is providing the stage. And because that stage is shared by everything, gravity becomes the ultimate organizer of motion over cosmic time. Not because it is strong, but because it never stops acting. This geometric framing also changes how we think about collapse. If gravity were a pull, collapse might be expected to happen quickly and directly. Matter would rush inward along straight lines, but geometry does not behave that way. It does not remove sideways motion. It does not erase existing trajectories. It only limits which paths remain stable as curvature increases. As a result, collapse becomes indirect. Matter drifts, turns, and reorganizes rather than falling straight inward. Paths curve. Motion persists. Energy redistributes. Geometry allows complexity to emerge instead of forcing immediate simplicity. Understanding gravity as geometry also helps explain why gravitational systems remember their past. Because geometry changes gradually, the history of how matter arrived where it is becomes embedded in the structure itself. Orbits, rotations, disks, and flows all carry information about earlier states. Gravity does not reset systems. It preserves continuity. This is the foundation for everything that follows in this walk. Once gravity is understood as shape rather than pull, slowness, rotation, disks, and staged collapse stop looking like special cases. They become the natural consequences of motion unfolding within a curved environment. In the next section, we will take the first of those consequences seriously. We will look at why gravitational collapse is usually slow, and why that slowness is not a weakness of gravity, but one of its most important features. Section 3. Why collapse is slow. Once gravity is understood as geometry rather than pull, the slow pace of collapse is no longer surprising. If nothing is being dragged inward, then nothing has any reason to rush. Matter responds only to the shape of space and time around it, and that shape changes gradually as mass redistributes. Collapse, in this view, is not an event. It is a long conversation between motion, energy, and geometry. Most matter in the universe begins in a diffuse state. Gas clouds are spread thin, particles move in many directions, and energy is not aligned toward any single outcome. When such a system begins to collapse, there is no moment where everything suddenly agrees on a center. The geometry does not issue a command. Instead, it gently biases motion. Paths that wander outward remain possible, but paths that drift inward become slightly more common. Over time, those small statistical preferences accumulate. This is why gravitational collapse typically unfolds over millions or billions of years. Geometry does not overpower motion. It reshapes the set of available paths. Each particle continues to move according to its own local conditions, but the overall environment slowly favors certain trajectories over others. Collapse emerges not because matter must fall, but because fewer stable options remain for staying dispersed. Energy plays a critical role in this slowness. Matter is never at rest. Particles carry thermal motion, turbulence, radiation pressure, and random velocities inherited from earlier processes. Geometry must work against all of this existing motion. It cannot cancel it instantly. Every inward step competes with pressure pushing outward, collisions redistributing energy, and radiation carrying heat away. Collapse proceeds only when geometry has enough time to outlast these competing effects. This also explains why collapse is uneven. Different regions of the same system can evolve at very different rates. Dense pockets cool and contract faster. Hot regions resist collapse longer. Some areas shed energy efficiently, while others remain supported by pressure. Geometry does not enforce uniformity. It allows local conditions to matter, and those differences stretch collapse out over time. Even when collapse accelerates, it does so gradually. There is no switch that flips gravity on. As matter gathers, curvature increases, and that increased curvature slightly biases motion further inward. This feedback exists, but it is gentle. Each step deepens the geometry a little more, and motion responds a little more strongly. The system evolves continuously, not catastrophically. The slowness of collapse is not a flaw in gravity. It is the reason structure can exist at all. If gravity acted as a strong pull, most matter in the universe would have collapsed early into dense, featureless clumps. There would have been little time for stars to form gradually, for disks to organize, or for complexity to emerge. Slow collapse creates space for other processes to operate alongside gravity rather than being overwhelmed by it. Time itself becomes an active participant in collapse. Geometry does not just shape where matter goes, it shapes how long transitions take. Collapse requires patience because geometry works by limiting paths, not by forcing outcomes. Matter must explore its options before finding itself constrained into more organized states. This is also why collapse often appears hesitant when viewed up close. Systems can hover near balance for long periods. Pressure, rotation, and radiation can temporarily counteract inward drift. From a short timescale perspective, nothing seems to be happening. But over long timescales, the geometry continues to do its quiet work. Small biases accumulate. Slow drifts become noticeable trends. Another important consequence of slow collapse is that motion has time to reorganize rather than disappear. Sideways motion is not erased. Random velocities are not instantly damped. Instead, they are redirected. As inward paths become more constrained, other components of motion begin to dominate. This is where new structures start to emerge, not as additions, but as survivors. Slow collapse also allows systems to retain memory. Because changes are gradual, earlier configurations leave traces in later ones. Density gradients, velocity patterns, and spatial asymmetries are not wiped clean. They are carried forward and transformed. Gravity does not reset systems, it evolves them. Understanding this slowness is essential for what comes next. Collapse does not move matter straight inward. It bends motion. It redirects trajectories. And as inward drift competes with persistent sideways motion, a new feature begins to appear almost everywhere in the universe. Rotation is not introduced, it is revealed. In the next section, we will look closely at why rotation emerges so reliably during collapse, and why it is not a coincidence or an initial condition problem, but a direct consequence of geometry allowing motion to persist while paths narrow. Section 4. Why rotation appears. As gravitational collapse proceeds slowly, motion does not disappear. It changes form. Geometry limits certain paths more than others, but it does not erase the motion that already exists. Because collapse is not a straight inward fall, any component of motion that is not perfectly aligned toward the center persists. Over time, those surviving components reorganize into rotation. In any realistic system, motion is never perfectly symmetrical. Particles move with slight differences in speed and direction. Even in the quietest gas cloud, there is turbulence, random velocity, and inherited motion from earlier interactions. When geometry begins to bias motion inward, it does not eliminate these sideways components. It simply restricts how they can be expressed. As inward paths become harder to maintain, sideways motion becomes comparatively easier. Matter cannot fall straight in without violating its existing motion, so it follows curved trajectories instead. These curves are not imposed. They are the natural result of geometry allowing motion to persist while narrowing the set of viable paths. This is where angular momentum becomes important, not as a rule imposed on the system, but as a description of what survives. Motion that already exists continues to exist unless there is a mechanism to remove it. Geometry does not remove angular momentum. It redirects it. As matter moves inward, its sideways motion occupies a smaller region of space, and that motion appears faster. Nothing new has been created. The same motion is simply being expressed in a more confined geometry. Rotation is therefore not added to collapse. It is what remains once straight inward motion is no longer available. The system is not choosing to spin. It is running out of alternatives that allow it to continue collapsing while respecting the motion it already has. This explains why rotation appears at nearly every scale in the universe. Molecular clouds rotate, stars rotate, planetary systems rotate, galaxies rotate. Even clusters of galaxies show coherent angular motion. This is not because the universe prefers spinning structures, but because geometry consistently channels persistent motion into rotation during collapse. The slower the collapse, the clearer this effect becomes. When collapse is gentle, motion has time to reorganize into coherent rotation rather than chaotic turbulence. When collapse is rapid, rotation can become disordered, but it still appears. Geometry never erases motion. It only reshapes it. Rotation also plays a stabilizing role. Spinning matter does not collapse straight inward. It spreads outward in some directions while drifting inward in others. This slows collapse without stopping it. Rotation allows systems to persist long enough for structure to form, rather than collapsing immediately into compact objects. Importantly, rotation does not oppose gravity. It is not a force pushing outward. It is a way for motion to coexist with geometric constraint. Collapse continues, but it does so along curved, extended paths rather than direct ones. Geometry and motion find a compromise. As rotation strengthens, it begins to define the shape of the system itself. Motion becomes organized around an axis. Inward drift is no longer isotropic. Some directions are favored over others. This is not because the system has decided on an orientation, but because rotation has narrowed the available paths even further. This process also carries memory. The axis of rotation reflects the history of how motion was distributed early in the system's evolution. Small initial asymmetries become amplified over time. Geometry does not average them away, it preserves them. Rotation is therefore not an accident or a detail. It is a structural consequence of slow collapse under geometric constraint. Once matter begins to gather and motion is allowed to persist, rotation is almost unavoidable. And once rotation becomes dominant, another transformation follows naturally. Matter no longer collapses into roughly spherical shapes. It spreads into extended, flattened structures that reflect the plane of rotation. Disks are not special cases. They are the next step in the same geometric story. In the next section, we will explore why disks form so reliably wherever collapse and rotation coexist, and why flattening is not a preference, but a consequence of which motions survive longest. Section 5. Why disks form. Once rotation becomes established, collapse changes its shape in a very specific and reliable way. Matter no longer has equal freedom to move in all directions. Motion aligned with the axis of rotation behaves differently from motion within the plane of rotation, and over time this imbalance reshapes the entire system. What begins as a loose, three-dimensional cloud gradually flattens into a disk, not because disks are preferred, but because they are what remain once geometry and motion have finished negotiating. The key idea here is that not all motion survives equally. In a rotating system, matter can move in three basic ways: inward or outward, sideways around the axis of rotation, and vertically above or below the rotation plane. Geometry constrains inward motion. Rotation preserves sideways motion, but vertical motion, over time, is the easiest to lose. Vertical motion is inefficient. When particles move above or below the plane of rotation, they tend to intersect with other flows, collide, radiate energy, or experience restoring influences that damp those excursions. Energy associated with vertical motion is shed more readily than energy associated with coherent rotation. As a result, matter slowly settles into the plane where its motion is most stable. This flattening is not sudden. It happens gradually, as countless small interactions remove vertical energy while leaving sideways motion intact. The system is not being pressed flat. It is relaxing into the configuration where motion can persist the longest without contradiction. Geometry does not flatten matter by force. It allows certain motions to fade while others survive. This is why disks appear almost everywhere collapse and rotation coexist. Protoplanetary disks around young stars, accretion disks around compact objects, galactic disks spanning tens of thousands of light years, and even ring systems all follow the same logic. They are not separate phenomena. They are expressions of the same geometric process operating at different scales. Disks also represent a compromise between collapse and persistence. In a disk, matter can continue drifting inward over long periods of time, but not all at once. Angular momentum must be redistributed. Some material moves inward while other material moves outward. This slow exchange allows collapse to proceed without destroying structure. Geometry does not demand immediate simplicity. It allows extended organization. Because of this, disks become sites of long-term evolution rather than endpoints. Within disks, matter has time to interact, cool, clump, and differentiate. Planets form in disks because disks provide stability without stasis. Stars feed from disks because disks regulate how material is delivered. Galaxies grow through disks because disks balance inflow and coherence. Another important feature of disks is that they store information. The structure of a disk reflects its history. Variations in density, temperature, composition, and motion all carry traces of how the system formed and evolved. Spiral patterns, gaps, warps, and rings are not random decorations. They are records written into matter by geometry over time. This means disks are not just shapes, they are memories. Gravity does not erase the past, it reorganizes it. Each stage of collapse leaves behind constraints that shape the next stage. Disks preserve those constraints in visible, measurable ways. It is also important to recognize that disks are not static. They are dynamic structures in slow motion. Matter continues to move, exchange energy, and evolve. Collapse has not stopped. It has been redirected. Geometry has traded a direct inward path for a longer, more structured route. This redirection is essential. Without disks, collapse would tend to be either too fast or too chaotic for complexity to arise. Disks slow the process without halting it. They allow systems to explore many configurations before reaching more compact states. In doing so, they create the conditions necessary for hierarchy, differentiation, and long-lived structure. Disks also make clear that gravitational collapse is not a single event. It is a sequence of phases. Diffuse matter gathers, rotation emerges, flattening follows. Each phase constrains the next. None of these steps are optional once geometry and motion are taken seriously. Even so, something remains incomplete. Within disks, matter still does not fall straight inward. Motion continues to curve, spiral, and circulate. Collapse proceeds, but always indirectly. To understand why, we need to look more closely at how geometry restricts straight-line motion itself. In the next section, we will examine why almost nothing in the universe falls directly toward a center, even when gravity dominates, and why curved paths are not deviations from collapse, but the only ones geometry allows. Section 6. How structure accumulates memory. By the time matter has gathered into rotating, flattened structures, something important has already happened. The system has begun to remember, not in a conscious sense, but in a physical one. Gravity, understood as geometry unfolding over time, does not erase history. It preserves it, reorganizes it, and embeds it into structure. Every stage of collapse leaves traces that shape what comes next. This happens because gravitational evolution is slow and continuous. When changes occur gradually, earlier configurations are not wiped away. They are carried forward. Paths taken in the past influence which paths remain available in the future. Geometry evolves smoothly, and motion adapts smoothly with it. The result is that structure becomes a record of how it formed. In a gravitational system, nothing resets to zero. Initial asymmetries matter. Small differences in density, motion, or composition can grow over time because geometry does not average them away. It constrains motion in ways that preserve those differences. A slight excess of mass in one region deepens curvature there, making inward drift slightly more likely in that direction. Over long time scales, that small bias can become a defining feature of the system. Rotation plays a key role in this memory-building process. Once an axis of rotation is established, it becomes a reference frame that persists. The orientation of disks, the alignment of orbits, and the distribution of angular momentum all reflect the system's early conditions. These features are not incidental. They are the physical imprint of past motion surviving into the present. Disks, in particular, act as memory reservoirs. Density patterns, temperature gradients, chemical compositions, and velocity structures all carry information about earlier stages of collapse. Spiral features trace instabilities. Gaps mark regions where matter was removed or reorganized. Warps record interactions with other structures or external influences. Geometry does not erase these features. It stabilizes them long enough to be observed. This is why gravitational systems often appear layered. Inner regions reflect later, more compact stages of collapse, while outer regions preserve earlier, more diffuse conditions. The system does not evolve all at once. It evolves outward in and inward out at the same time, accumulating history rather than overwriting it. Memory is also stored in motion itself. Orbits encode past interactions. Eccentricities reflect earlier perturbations. Resonances capture the influence of long-lived geometric constraints. Even chaotic motion carries statistical information about the shape of the underlying spacetime. Nothing moves randomly in a gravitational system. Motion always reflects constraint. Importantly, this memory is not fragile. Because it is embedded in geometry and motion, it can persist for enormous lengths of time. Planetary systems retain signatures of their formation billions of years later. Galaxies carry structural records of mergers and accretion events long after those events have passed. Gravity allows history to remain legible. This accumulation of memory is one reason gravity is so effective at producing complexity. Systems that remember their past can build on it. Each stage of evolution provides constraints and resources for the next. Collapse does not erase structure. It reorganizes it into new forms that still carry the imprint of what came before. This also explains why gravitational systems are rarely simple. Even when governed by a single underlying principle, the outcomes are rich and varied. Geometry does not force systems toward a single ideal state. It allows many long-lived configurations to coexist, each reflecting a different history. Memory accumulation also means that collapse is irreversible in practice. Even though the underlying laws are time-symmetric, the path a system takes through configuration space leaves a trail. Returning to an earlier state would require undoing an enormous amount of accumulated structure and motion. Geometry does not prevent this in principle, but it makes it extraordinarily unlikely. As systems continue to evolve, this accumulated memory begins to organize collapse into distinct phases. Certain configurations persist for long periods, then give way to others as constraints tighten. Collapse does not happen smoothly from start to finish. It proceeds in stages, each one shaped by the memory left behind by the previous stage. In the next section, we will look at this staging directly. We will explore why gravitational collapse tends to unfold in recognizable phases rather than as a single continuous slide, and how geometry and memory work together to create natural thresholds in evolution. Section 7. Why collapse has stages. By the time structure has accumulated memory, collapse no longer unfolds as a smooth, uniform process. Instead, it begins to separate into phases. Certain configurations persist for long periods, then give way to new ones once specific constraints are met. Collapse does not flow continuously from diffuse matter to compact objects. It moves through stages, each shaped by geometry, motion, and the memory already embedded in the system. This staging emerges naturally from the way geometry limits motion. At any given moment, a gravitational system occupies a region of configuration space defined by its mass distribution, energy, angular momentum, and geometry. As long as there are stable paths available within that region, the system can persist in its current form. Collapse advances only when those paths become restricted enough that the system must reorganize. Early in collapse, diffuse matter can remain loosely bound for long periods. Pressure, turbulence, and radiation balance inward drift. Geometry is curved, but not enough to eliminate many of the available trajectories. The system evolves slowly, with small changes accumulating over time. This is the first stage, where gathering occurs without dramatic restructuring. As matter continues to collect and geometry deepens, some paths begin to disappear. Certain motions become harder to sustain. Cooling allows energy to be shed, and pressure support weakens. At this point, the system enters a new stage. Collapse accelerates locally, but not globally. Dense regions evolve faster, while outer regions lag behind. The system fragments, differentiates, and develops internal structure. Rotation and disk formation mark another stage boundary. Once angular momentum dominates motion, collapse changes character again. Matter no longer moves freely in three dimensions. Motion becomes constrained to planes and curved trajectories. Disks persist for long periods, regulating inflow and redistributing angular momentum. This stage can last millions or billions of years, depending on scale. Each of these stages is separated not by external triggers, but by internal thresholds. Geometry reaches a point where certain configurations are no longer stable. Motion reorganizes. A new balance emerges. Collapse does not jump, it transitions. These transitions are often mistaken for events, but they are better understood as shifts in constraint. Nothing dramatic has to happen. No new force appears. Geometry simply tightens. Paths that once existed no longer do. The system adapts by finding a new way to persist. Memory plays a crucial role here, because earlier stages leave behind structure, later stages inherit constraints. Angular momentum accumulated early on shapes how later collapse proceeds. Density gradients established in one stage define fragmentation patterns in the next. Geometry does not forget where it has been. This stage nature of collapse also explains why gravitational systems exhibit hierarchy. Smaller structures form within larger ones. Cores develop inside disks. Planets form within disks around stars that themselves formed within clouds inside galaxies. Each level of structure reflects a stage that stabilized long enough to become the foundation for something else. Staging also introduces irreversibility. Once a system has crossed a threshold, returning to an earlier stage becomes increasingly difficult, not because it is forbidden, but because it would require undoing accumulated memory. Geometry does not lock doors. It simply makes certain paths impractical. Another important consequence of staged collapse is that extreme outcomes are delayed. Compact objects do not appear immediately. Systems linger in intermediate configurations where energy can be radiated, angular momentum redistributed, and structure elaborated. These intermediate stages are not inefficiencies. They are the mechanism by which complexity arises. Understanding collapse as staged rather than continuous also reframes how we think about stability. Stability is not the absence of change. It is the persistence of a configuration within a given set of constraints. A disk can be stable for billions of years while still evolving internally. A star can remain stable while slowly burning fuel. Geometry allows stability and change to coexist. As collapse proceeds through successive stages, the range of available configurations narrows. Eventually, systems approach limits where further reorganization becomes difficult without radical change. This is where extreme objects begin to appear, not as shortcuts through collapse, but as endpoints where geometry has exhausted its options. In the next section, we will look closely at these extreme outcomes. We will explore why objects like neutron stars and black holes are not dramatic violations of the gravitational story, but natural conclusions of a long sequence of geometric constraints unfolding over time. Section 8. Why extreme objects are endpoints, not shortcuts. By the time a gravitational system approaches what we call an extreme object, most of the work has already been done. The geometry has tightened, options have narrowed, and motion has been redirected again and again through earlier stages. Neutron stars and black holes do not appear because gravity suddenly becomes violent or impatient. They appear because there are no remaining configurations that allow the system to persist in any other way. It is common to think of these objects as dramatic failures or sudden collapses, as if gravity takes a shortcut and rushes matter into an extreme state. But this framing misses what actually happens. Extreme objects are not accelerations of collapse. They are conclusions. They occur only after collapse has exhausted every slower, more structured alternative. Throughout earlier stages, matter sheds energy, redistributes angular momentum, and organizes itself into extended forms. Disks regulate inflow. Rotation slows collapse. Pressure and quantum effects resist compression. Each of these mechanisms allows the system to persist longer, buying time for structure to develop. Extreme objects form only when these mechanisms can no longer maintain stable paths. At this point, geometry leaves the system with very few options. Matter can no longer rearrange itself into a configuration that balances motion, pressure, and curvature. Collapse does not speed up because gravity has changed. It speeds up because there are no remaining paths that allow gradual evolution. Consider neutron stars. They form when matter is compressed to densities where atomic structure can no longer survive, but where collapse is still resisted by quantum effects. This resistance does not halt collapse arbitrarily. It defines a new stage. Neutron stars are stable because geometry, motion, and quantum pressure find a temporary balance. They are not intermediate steps on the way to black holes. They are endpoints in their own right, representing the last configuration available before geometry tightens further. Black holes appear only when even these balances fail. They are not objects in the usual sense. They are regions where space-time curvature becomes so dominant that the distinction between space and time itself changes character. Motion no longer has the degrees of freedom it once did. Paths that once allowed persistence simply no longer exist. Importantly, black holes do not represent gravity becoming stronger. Gravity has not turned up its intensity. Geometry has become so constrained that escape paths disappear. Matter does not fall in because it is pulled harder. It falls in because there are no trajectories left that allow it to remain outside. This is why black holes should be understood as endpoints rather than shortcuts. They mark the boundary where geometry has removed all alternative configurations. Collapse cannot be slowed further because nothing remains to slow it. Time itself becomes entangled with spatial direction, and persistence takes on a new meaning. Extreme objects also preserve memory, but in a compressed form. Neutron stars retain information about rotation, magnetic fields, and composition. Black holes retain information in subtler ways, encoded in mass, spin, and charge, and possibly in deeper geometric structures still being explored. Even here, gravity does not erase history. It hides it behind constraints. Another important point is that extreme objects are rare relative to the amount of matter in the universe. Most matter never reaches these endpoints. It remains in stars, disks, galaxies, and diffuse structures for billions of years. This rarity is not accidental. It reflects how many stages collapse must pass through before extreme configurations become unavoidable. Thinking of extreme objects as shortcuts also encourages a misleading sense of drama. In reality, the formation of a black hole is often the quiet outcome of a long process. From the system's own perspective, nothing sudden occurs. Geometry simply removes the last available detours. Understanding this reframes how we think about gravity's role. Gravity is not a destroyer rushing systems toward singular states. It is a sculptor that patiently removes possibilities until only one remains. Extreme objects are the points where sculpture is complete, not where it becomes reckless. This perspective also prepares us for the next step in the walk. If geometry can constrain motion to such an extent that even time is reshaped, then gravity is not just influencing where things go. It is influencing how duration itself is experienced. To see that clearly, we need to talk about how gravity reshapes time. In the next section, we will explore gravity's relationship with time and why collapse is not just a spatial process, but a temporal one as well. Section 9. How gravity reshapes time. By the time we reach this point in the walk, it becomes impossible to keep talking about gravity as if it only affects where things go. Gravity reshapes time just as deeply as it reshapes space, and the two cannot be separated. Geometry is not a backdrop that matter moves through while time ticks independently in the background. Space and time are part of the same structure, and when geometry curves, duration itself changes. This is one of the most counterintuitive aspects of gravity, because we experience time as steady and uniform in our daily lives. Seconds pass at the same pace whether we are sitting still or walking across a room. That familiarity makes it easy to forget that time is not absolute. It is shaped by motion and by geometry in the same way paths through space are shaped. In a gravitational system, time does not pass at the same rate everywhere. Where geometry is more strongly curved, time runs more slowly relative to regions where curvature is weaker. This is not a mechanical effect, and it is not caused by forces acting on clocks. It is a geometric consequence. The paths that clocks follow through space-time differ depending on where they are embedded in the overall structure. This slowing of time is not something that turns on suddenly near extreme objects. It happens everywhere gravity is present. Near Earth, the effect is small but measurable. Satellites experience time slightly differently than clocks on the ground, and systems like GPS must account for this difference to function correctly. Geometry is already shaping time in subtle ways all around us. As collapse proceeds and geometry deepens, these temporal effects become more pronounced. In regions where matter is dense and motion is constrained, time stretches relative to regions farther out. Processes slow down. Transitions take longer. From the outside, evolution appears to decelerate as systems approach more compact configurations. This has a profound implication for how collapse unfolds. As geometry tightens, not only do spatial paths narrow, but temporal paths stretch. The closer matter gets to extreme configurations, the more time itself resists rapid change. Collapse does not race toward its conclusion. It asymptotically slows from the perspective of distant observers. This is why black holes appear to freeze objects at their boundaries when viewed from far away. It is not because something dramatic happens at a specific surface. It is because time itself is being reshaped by geometry. Paths through space-time tilt in such a way that outward communication becomes increasingly delayed. Gravity does not stop clocks. It changes how clocks relate to one another. Time dilation also reinforces the staged nature of collapse. Each stage persists not only because spatial configurations are temporarily stable, but because time stretches within them. Processes slow, allowing systems to linger in intermediate forms. Gravity gives structure time to exist by reshaping duration itself. This also means that gravity controls not just motion, but rates. Chemical reactions, nuclear processes, and dynamical evolution all proceed at different effective speeds depending on where they occur within a gravitational field. Geometry sets the tempo of the universe. Understanding this helps resolve a common misconception. Gravity is often thought of as accelerating things, making them move faster. In reality, gravity often does the opposite. It slows evolution by stretching time. Objects may gain speed in space, but the overall progression of states becomes more gradual. This temporal shaping is essential for persistence. If gravity only curved space without affecting time, collapse would be far more abrupt. Systems would move inward quickly without the opportunity to reorganize. By stretching time where curvature is strong, gravity allows systems to approach limits without crossing them immediately. Time reshaping also preserves memory. When evolution slows, information has time to settle into structure. Motion patterns stabilize. Configurations persist. Gravity does not just constrain motion spatially. It gives structure the temporal room it needs to become legible. Seen this way, gravity is not just the architect of structure, but the keeper of duration. It decides not only what paths are available, but how long systems can remain on them. Persistence is not accidental. It is built into the geometry. This reframes extreme objects yet again. Near the endpoints of collapse, time becomes so distorted that the usual notion of sequence breaks down. From the outside, evolution appears to stall. From the inside, paths continue, but they lead inexorably inward. Gravity does not end time, it folds it into geometry. This brings us naturally to the final outward-looking question. If gravity shapes both space and time so deeply, then it is not just governing local collapse. It is influencing the long-term evolution of the universe itself. To complete this walk, we need to step back and ask what gravity is doing on the largest time scales of all. In the next section, we will look at gravity's role in the far future and how patient geometry continues to shape persistence long after the familiar structures of the universe have changed. Section 10. Gravity in the Far Future. What patient geometry does over cosmic time. 1. When we talk about gravity shaping the far future, we are really talking about a slow contest between two kinds of behavior. One kind gathers, the other kind separates. Gravity gathers matter into bound systems, tightening curvature locally, building long-lived structures, and turning diffuse possibility into organized persistence. But the universe is also expanding, which means that on the largest scales, distances between unbound regions grow. Over time, this expansion changes what gravity can still reach, not by weakening gravity as a law, but by stretching the arena in which gravity can act. This is the first important shift to keep in mind. The far future is not a single event. It is an ongoing sorting process. Gravity does not stop working, but the universe gradually divides into two categories of places. There are regions that become gravitationally bound and remain in causal contact, and there are regions that drift away beyond practical influence. The future is shaped by what stays connected long enough to keep exchanging matter, energy, and information. Gravity's role on the largest scales is to decide what remains a together system and what becomes permanently elsewhere. In the early universe, structure formation was easy in a certain sense. Matter was more uniformly distributed, distances were smaller, and the cosmic web could grow rapidly. Small density differences had time to amplify into large structures. But as the universe expands, the average density drops, and the growth of new structure becomes harder. There is less raw material per volume, less opportunity for new regions to become bound, and fewer collisions between large systems. Gravity still tries to gather, but it increasingly works with what it already has. This leads to a quiet but powerful prediction about the far future. Most of the dramatic building is front-loaded. The universe does much of its large-scale organizing early and then spends the rest of its time refining, stabilizing, and aging what is already formed. Galaxies merge early and often, then less often. Star formation peaks, then declines as gas is used up or heated, locked into remnants, or pushed into configurations that no longer cool efficiently. Gravity continues shaping, but it shifts from building new toward rearranging old. That does not mean nothing happens. It means the tempo changes. Just as we saw in collapse, gravity does not rush. It narrows possibilities slowly. In the far future, what changes is not gravity's rule, but the availability of fresh pathways for gravity to express itself. Another way to say this is that gravity tends to make islands. Bound systems become long-term archives of structure and memory. A galaxy group, a cluster, a local neighborhood of galaxies, these become the durable containers where complexity can persist. Outside those containers, the universe becomes increasingly empty, increasingly dilute, and increasingly difficult to reorganize. This island making has a geometric character. Within a bound system, space-time curvature and motion remain deeply coupled. Orbits remain meaningful. Mergers remain possible. Energy can be exchanged. But between islands, expansion stretches the space-time separation faster than gravity can meaningfully overcome. It becomes less and less likely that a distant structure will ever meet another structure again. The cosmic web, in a sense, stops knitting new threads and begins slowly freezing into the pattern it already has. From the perspective of persistence, this is a profound shift. Persistence does not mean everything lasts. It means that some configurations are allowed to survive longer than others. Gravity allows local survival by building bound systems, but it also allows global separation by permitting the expansion to carry unbound regions apart. The far future is gravity's patient geometry, continuing to sculpt what is still possible, but under a changing backdrop of connection. This is where the question of the universe's long-term expansion matters. We do not need to resolve every cosmological debate to see the logic. If the universe continues expanding at an accelerating rate, then over immense time, more and more of the universe becomes causally inaccessible. Distant galaxies fade, not because they are destroyed, but because the geometry of space-time changes the relationship between motion and communication. The observable universe becomes a smaller and smaller fraction of what exists. The night sky simplifies. The record becomes harder to read from any single location. In that scenario, gravity's future work becomes increasingly local. It governs what happens inside bound islands, how stars age and die, how remnants drift and interact, how black holes grow, how energy is redistributed, how systems relax toward quieter configurations. But gravity becomes less able to create new large-scale structure across the widening gaps. The universe becomes a set of long-lived, slowly evolving pockets, separated by distances that functionally never shrink. Even this is not a dramatic ending. It is a geometric consequence. Gravity does not fail. The arena changes. Inside those bound regions, the story continues in the way we have already learned to recognize. In stages, with memory, with slow reorganizations. Star formation eventually declines as the easy fuel is spent. The bright era of abundant new stars gives way to an era dominated by stellar remnants, white dwarfs cooling, neutron stars spinning down, black holes quietly interacting with their surroundings. The most violent episodes become rarer simply because there are fewer fresh resources and fewer encounters. Over time, bound systems tend to relax. Orbits become more stable or more dispersed. Energy finds its way into channels that are hard to reverse. This is a future where persistence still exists, but it changes flavor. Early on, persistence looks like construction, clouds becoming stars, disks becoming planets, galaxies building structure. Later, persistence looks more like endurance, long-lived remnants, slow interactions, faint emissions, rare mergers, gradual drift. Gravity remains the organizer, but the materials it organizes become harder, colder, and less pliable. And this is an important honesty point. We cannot narrate the far future with absolute certainty because it depends on deep questions about dark energy, long-term stability of physical laws, and the behavior of matter under extreme timescales. But we can still describe the shape of the reasoning. Gravity does not need a script. If the universe keeps expanding and matter keeps thinning, then the future becomes more sparse. If bound systems remain bound, then the future becomes more local. Either way, gravity continues to sort what persists from what disperses. There is also a subtle connection here to time, the thing we just discussed. In the far future, time is not merely more of the same. It becomes the medium through which structure either remains legible or fades into statistical quiet. When the universe is rich with interactions, time is full of events. When interactions become rare, time becomes wide. The intervals between meaningful reorganizations grow. A universe can be changing while still feeling still, simply because its characteristic processes stretch out beyond intuitive scales. That is one of the quiet lessons of gravity. It is not only about motion, it is about the spacing of change. Gravity shapes the cadence at which systems can transition, and in the far future that cadence slows, not because time stops, but because there are fewer paths left that lead to large visible change. And in that sense, the far future is an extension of everything we have already said. Collapse is slow because geometry limits paths rather than forcing outcomes. The far future is slow for the same reason. The universe is not rushing toward an ending. It is gradually exhausting the easy pathways for new structure to form, while continuing to preserve and refine the structures that already exist. This also reframes how we think about the words end and final. The universe may approach conditions that feel like an ending from a human perspective: coldness, sparsity, darkness, long intervals, but geometrically it is still a process. Bound systems still have internal motion. Black holes still interact. Particles still follow paths. Fields still fluctuate. The story continues, but the tone shifts from building to lingering. If gravity is the keeper of duration, then the far future is where that becomes most obvious. Gravity does not merely assemble things, it determines how long assembly remains possible and how long the assembled structures can endure. It decides which configurations can remain stable in an expanding space-time and which ones can no longer be sustained. Persistence is never free. It is granted by the availability of stable paths, and those paths become rarer over time. The reason this matters for our walk is that it closes the loop. We started by saying gravity is not an event, but a process. The far future is the ultimate proof of that framing. Gravity is not a dramatic episode in the universe's history. It is the long-term geometry through which the universe sorts itself into what can remain coherent and what cannot. And that prepares us for the closing. If gravity is patient geometry, then the deepest thing we can say about it is not that it pulls. It is that it organizes. It decides what stays connected, what becomes isolated, what survives in structured form, and what dissolves into thinness. It shapes both motion and memory, both space and time, both local systems and the universe's long arc. In the next and final section, we will bring all of this back to the human scale of understanding. We will summarize what this walk has shown, not as a final theory, but as a clear way of seeing gravity that makes the universe feel more legible, not louder, not more dramatic, just more consistent. Section 11. Closing, walking the geometry together. As we come to the end of this long walk, it's worth pausing to notice how different gravity may feel now compared to when we started. Not louder, not more dramatic, just clearer. Gravity is no longer a force rushing objects around the universe. It is a patient geometry that shapes what motion is possible, how structure forms, and how long things can last once they do. Throughout this walk, we didn't need gravity to make decisions or issue commands. We didn't need it to pull, threaten, or accelerate the universe toward outcomes. All we needed was shape. Matter exists, geometry responds, motion follows. Over time, constraints accumulate, options narrow, and structure emerges. Not because the universe is trying to build something, but because geometry quietly limits what can persist. When collapse is slow, it is not because gravity is weak. It is because geometry works by narrowing paths, not by forcing outcomes. When rotation appears, it is not because systems choose to spin, but because sideways motion survives where straight inward motion cannot. When disks form, it is not because flat shapes are preferred, but because vertical motion fades faster than coherent rotation. When structure accumulates memory, it is not because the universe remembers intentionally, but because slow change preserves history instead of erasing it. Even the most extreme objects we know fit naturally into this picture. Neutron stars and black holes are not shortcuts or breakdowns. They are endpoints reached only after geometry has exhausted every other option. They appear not because gravity becomes violent, but because persistence has run out of alternatives. And when gravity reshapes time itself, slowing evolution and stretching duration, it does so for the same reason it reshapes space. Geometry is the rule everything must follow. Taken together, this changes how we think about the universe. Structure is not imposed, it is permitted. Complexity is not designed, it is allowed to survive. Persistence is not accidental, it is a consequence of constraints unfolding slowly enough for patterns to take hold. This way of seeing gravity also changes how we think about our place in the universe. We are not standing in opposition to gravity, struggling against it. We are embedded within it. Every stable structure we rely on, from planets to stars to galaxies, exists because geometry made room for it. Even the passage of time we experience is shaped by the same quiet rules. Nothing in this story required gravity to be special in a dramatic sense. Its power comes from consistency. Geometry never turns off. It never gets tired. It never skips steps. Given enough time, it will explore every allowable path, and in doing so, it will build structure wherever persistence is possible. This is why gravity serves as the structural backbone of the PIW-CWG framework. It is not just one interaction among many, it is the condition under which all long-term structure exists. It governs how information accumulates, how entropy is paid, and how systems move from possibility to persistence without ever needing a script. If there is one idea to carry forward from this walk, it is this: gravity does not make things happen. It makes some things unavoidable over time, and by doing so, it allows the universe to become legible, layered, and meaningful without ever being instructed to do so. Thank you for taking this long walk with me. I know this was not a short or simple conversation, and I appreciate the patience it takes to slow down and think this way. If this perspective on gravity resonated with you, or if it raised questions you'd like to explore further, feel free to share your thoughts in the comments. These ideas grow stronger through careful conversation. If you found value in this video, please consider liking it, sharing it, or subscribing to the channel. This episode is part of the broader PIW-CWG series, where we explore how persistence, information, and constraint shape the universe from the smallest scales to the largest ones we can imagine. My name is Charles Carroll, and thank you for joining me on this cosmic walk.